Section: Introduction. In this section, we discuss the advancements made by large language models, LLMs, in natural language processing, noting their impressive performance across various tasks. However, we recognize that the inner workings of these models are not fully understood, which complicates our ability to improve their performance and interpret their predictions. While some recent studies have started to reveal certain patterns within LLMs, key aspects like step-by-step reasoning and long-range dependencies remain unclear. This lack of understanding limits our progress in creating more interpretable and efficient language models. To address this issue, we introduce LLM-Microscope, a framework aimed at analyzing and visualizing the internal behaviors of LLMs. Our toolkit includes methods for examining how models handle contextual information. We assess contextualization to identify which tokens carry the most context, measure nonlinearity at the token level to see how closely transformations between layers can be simplified, and analyze how next token predictions change across layers using a technique adapted for multimodal LLMs. By applying these tools in various scenarios, we uncover interesting patterns in how LLMs process information. For instance, we find that certain filler tokens, like punctuation and stop words, are crucial for understanding language and that their removal negatively impacts performance on tasks requiring specialized knowledge and longer context. LLM-Microscope is designed to be user-friendly for both researchers and practitioners, offering an intuitive interface for detailed model analysis. In terms of related work, we note that there are different approaches to model interpretability. Probing methods train classifiers based on hidden representations but do not analyze internal representations during knowledge activation, leaving much of the model's behavior unclear. On the other hand, mechanistic interpretability focuses on exploring the internal workings of models through neuron activations and layer connections. Research in this area often examines how model behavior changes with perturbations or noise. Sparse autoencoders have emerged as a promising method for discovering interpretable features in LLMs, focusing on specific components like attention heads. We also highlight the interest in studying the internal structure of transformer-based models, with techniques like logit-lens, projecting intermediate layer representations into vocabulary space. Our work builds on this by exploring the linearity of hidden representations and analyzing how contextual information is embedded in these models. LLM-Microscope serves as a comprehensive framework for analyzing LLMs. We have created a demo system using Gradio, hosted on Hugging Face, which allows for interactive exploration of our analysis methods. Users can select from various pre-loaded models, input custom text, and visualize results, including heat maps of token-level nonlinearity and contextualization levels. Our system provides insights into the model's reasoning process, and for those seeking deeper analysis, we have made our entire codebase available. Section Summary. In this section, we introduce LLM-Microscope, a framework designed to analyze and visualize the internal mechanisms of large language models, LLMs, addressing the challenges of interpretability and contextual understanding. Our toolkit provides methods to assess contextualization, token-level nonlinearity, and intermediate layer contributions, revealing the significant role of seemingly trivial tokens in model performance and offering an accessible interface for researchers and practitioners. Section: Measuring Token-Level Nonlinearity. In this section, we measure the nonlinearity of token representations across model layers. We use a generalized Procrustes analysis to assess how linear transformations affect adjacent layers. For each pair of layers, we find the best linear transformation and calculate the nonlinearity score for each token based on their embeddings. Next, we evaluate the contextual memory in token-level representations. We propose a method that examines how well the model can reconstruct prefix information from individual token representations. This involves processing an input sequence through the model, gathering hidden states, and combining these into a single representation using a trainable pooling layer followed by a two-layer MLP. We train this system to reconstruct text fragments using various datasets. The effectiveness of this reconstruction is measured by the cross-entropy loss, where a lower score indicates better contextualization. We also track how token predictions evolve across the model's layers. By collecting hidden states and applying the language model head, we compute token probabilities and prediction errors for the next token. This analysis reveals how prediction accuracy changes and when the model makes its predictions. To visualize these predictions, we implement the logit lens technique, which shows how token predictions develop across layers. This method generates probability distributions over the vocabulary, illustrating the model's evolving beliefs as it processes input. Finally, we assess the intrinsic dimensionality of token representations to understand their complexity and information content. We estimate how the volume of an n-dimensional sphere scales with dimension, using distances to the nearest neighbors to compute the intrinsic dimension. Section Summary. In this section, we measure token-level nonlinearity using generalized Procrustes analysis to assess the linearity of token representations across model layers, and we quantify contextual memory by reconstructing prefix information from token embeddings, evaluating contextualization through cross-entropy loss. Additionally, we analyze the evolution of token predictions across layers and visualize these predictions using the logit lens technique, while also estimating the intrinsic dimensionality of token representations to understand their complexity and information content. Section: The most memory-retentive tokens. In this section, we analyze how different types of tokens retain and encode contextual information. We processed random snippets from Wikipedia articles through our pipeline, collecting contextualization scores for all tokens while keeping track of the original words before tokenization. Surprisingly, we discovered that the tokens most useful for reconstructing context, like prefixes, are often the least semantically significant, such as determiners, prepositions, and punctuation marks. In contrast, nouns and adjectives are more difficult to use for prefix reconstruction. This unexpected result implies that language models might rely on these seemingly minor words to aggregate memory or overall meaning. Across all models we examined, including various sizes of the opt, phi, and llama families, determiners and punctuation consistently showed the highest contextualization with the lowest reconstruction loss scores. Conversely, nouns appeared among the least contextualized tokens, with much higher reconstruction loss values. We also explored how removing filler tokens impacts the performance of language models on tasks requiring domain knowledge or extended context. Instead of removing highly contextualized tokens, we selectively eliminated punctuation, stop words, and articles using two methods: a simple rule-based removal and a more refined approach using GPT-4o. For our benchmarks, we evaluated these removal strategies on two tests: MMLU, a multiple-choice benchmark covering various academic subjects, and BABILONG4K, which combines facts and large amounts of distractor text. We examined several removal conditions, including deleting common function words, punctuation marks, and articles, as well as a combined approach and a selective removal using GPT-4o. Our results showed that removing punctuation and basic function words consistently decreased performance. In BABILONG4K, where capturing subtle facts is crucial, the accuracy losses were particularly significant. These findings align with our earlier observations that language models often store key contextual signals in filler tokens, which may seem unimportant. Even a careful removal strategy via GPT-4o highlighted the importance of these tokens in maintaining context, especially in long sequences or academic questions. We also found a strong correlation between layer-averaged linearity and contextualization scores for individual tokens. Tokens with high contextualization often corresponded to the most linear transformations across layers. This relationship was consistent across different model architectures and sizes, suggesting a link between a model's ability to retain contextual information and the linearity of its internal representations. Lastly, we used the logit lens technique to investigate how language models handle non-English input. Our analysis revealed that intermediate layer representations mainly correspond to English tokens, even when the input is in another language. The heat map we created showed that correct non-English tokens gradually appeared in later layers, indicating that the models might perform implicit translation into English before generating the final output.